Hello children, welcome back to the channel. Today we will be taking up a very important topic of system of particles. Now, up till now when we have been discussing physics or class 11th level physics, what we have discussed is about the motion of bodies, right? Uh, First we discussed about the motion of bodies without discussing the cause of motion. Then we moved on to Newton's laws of motion, where we discussed what caused a body's motion or bodies to move, or what caused the bodies to accelerate and all. And then we spoke about work, energy and power. Now, while doing all these discussions, what we have done is that we have taken different types of bodies. Say we have spoken about blocks of wood or balls or bullets or different bodies, and we have said that a force is applied, and then when we say the force is applied to a body, say a force of F is applied to somebody, and so the body achieves certain motion maybe in a straight line or in a plane, but it took a translational motion, that is, it moved from one point to another. It traveled from one position to another position, right? Its position changed. Now, while doing so, what we have done is that we have taken extended bodies, but we have taken that the force is applied. Say we had said that force is applied to it, and then there is a frictional force which will be in the opposite direction. The points of applications are different. Then what we did is that when we did the analysis, we said that the force is in this direction, and then the friction was in this direction. So we have considered a single point where the forces are being applied. We didn't consider the extended bodies as a whole, because it was not necessary at that particular point of time. However, in real life we come across different types of bodies, wherein you can say we have a body like this. Say there is a mass here, there is another mass here, and they are connected through a rod. Now when an external force is applied to it, where shall we consider the force is applied? To this particular mass, or to this particular mass, or to the rod? Where exactly? So it becomes a little complicated for us, and this is what we are going to discuss. This is a system of particles. Now first of all, when we say system of particles, before getting into the term system, we need to understand what is a particle. What do we mean by particle? Now in physics, the term particle defines to a mass, say m, a finite amount of mass. However, the dimension of the mass is said to be negligible. So what we mean by particle is that we are basically considering a point object, an object which has certain finite mass, but it doesn't have any dimensions, because we know from mathematics that something that has its position but it doesn't have any length or breadth or any dimension, then it is known as a point. So a particle basically means a point mass. It has a finite magnitude of mass, but its dimension is said to be negligible. So system of particles will be a collection of such masses. Say there is one mass here, there is another mass here, there is a third mass here. Okay, so these three masses will form a system of particle. However, they will not form a system of particle just like that. These three masses, let's call them 1, 2 or 3. So these three masses, we will from now on we will call them particles, because we have already defined them as particles, right? So what must happen is that these particles must interact with each other. There must be mutual interaction between the particles. If we have a number of particles having mutual interaction between them, such that their positions relative to each other are not altered upon application of some external force. If we apply a force from outside, the particles will hold their position with respect to one another. Okay, in such case, these three particles together will be called a system of particles. So a system of particles can have a huge number of particles. However, these particles must have mutual interaction between them, and they should have no relative position with respect to each other. We have said three, we can have multiple more number of particles, right? Any number of particles we want. If all these particles have interaction among themselves, then have a mutual interaction. Interaction not from outside, from inside each other due to gravity or any other kind of bond, chemical bond or whatever. If they interact with each other, we call them a system of particles. So system of particles is what we are going to discuss now. Now, these systems of particles are held together by their mutual interactions. What are mutual interactions? They are nothing but forces. So, there will be a force on 2 due to 1, say F2, 1. There will be a force on 1 due to 2. There will be a force on 3 due to 1. There will be a force on 3 due to 2. There will be a force on 2 due to 3. There will be a force on, say, 1 due to 3. So, there are forces of interaction between them. And these forces of interaction, which are not supplied from outside, but are internal to the system of particles. Such forces are known as internal forces. So internal forces are forces within the system of particles which keep the system intact. It is not dependent, or it is not, these forces are not dependent on external agencies, and they are not influenced by external agencies. Okay, now then if we want to impart some motion to the system of particles, say these three particles together, they will form a system, and we want to impart some motion, then we will have to put some force from outside. We know for motion to occur or state of motion to change, force needs to be applied. Newton's laws of motion. You can find it in any books, or you may also refer to my playlist on Newton's laws of motion. The link will be given in the description below. So, an external force needs to be applied to the system of particles so that they move. So whatever force is applied from outside to cause translational motion to a system of particles is known as external force. These are few important terms we are going to use while we continue our discussion of system of particles. What are the important definitions? Definition of particle: what is a particle? What is a system of particle? What are internal forces? And what are external forces? Okay. Now we are going to define another very, very important term, and that is center of mass. Now, what is center of mass? First of all, we need to find why we need to define a term known as center of mass. See, we have seen in this that there are a lot of forces acting on it. And also, if we neglect the internal forces because they do not cause any kind of motion, so if we do not write this, still in this system of particles, the three particles, when we apply the force from outside, the external force, the system will behave in certain way, right? We do not know. And it's difficult for us to apply Newton's laws, because for this we have to apply Newton's law to 1. When we apply a part of a force to point 1, it will tend to move, but it is already connected to point 2 and point 3 also, so other particles also. So what will happen? They will also influence its motion. Similarly, the force acting on second particle also will get affected by first and third particle, and so on. So what we have is that this system, because of the mutual interaction, it becomes a little difficult for us to apply Newton's laws directly. So to be able to apply Newton's law directly, we need to call in the help of a concept known as center of mass. Now what is center of mass? By definition, by the term itself, you can say that center of mass is the mass center, or the center point where the mass is concentrated. So if we have to define it in words, what we will say is that center of mass is that point where we can consider the entire mass of the system of particles to be concentrated. So let us say this is M1, this is M2, and this is M3. So entire mass is equal to M equals to M1 plus M2 plus M3, right? So there will be a point somewhere, we do not know where, we will have to find it mathematically, where the entire mass of the system can be supposed to be concentrated. Now how does it help? This particular point has a special property, or must have a special property, and what is it? That when this external force acts on the system of particles, the system of particles will move, right? And let's say it moves in a path like this. This is the trajectory the system of particles takes under the influence of the external force. Then by definition, center of mass is that point where if we put a mass equal to the sum of the three masses and apply the same force to it, it will follow the same trajectory as the system with the distributed mass. Are we clear about this? So basically what we are saying is that center of mass is the particle equivalent of the system of particles. So in the system of particles there were three particles, and we applied a force, it followed a particular path following Newton's laws, which is difficult to be applied, right? Center of mass is a point in space, it's a position where if we say that we consider all the three masses, that is sum all the three masses and form a particle and put it at that particular position, then and apply the same external force, then it will follow the same path as the extended body or extended system of particles would have done. Okay. So center of mass becomes a very, very important topic for us to understand, and to be able to apply Newton's law, we should be able to find the center of mass of these systems of particles. This is what we are going to do next. Alright, now let us consider a two-particle system. What we are going to try is to find where the center of mass of this two-particle system will lie. First, let's say first particle is at point P1 and has a mass of M1. Second particle, let's say, is at point P2 and has a mass of M2. So the position vector of point P1 we will call this R1, and of point P2 is R2. So particle 1 has a position vector of R1 and particle 2 has a position vector of R2. There will be a mutual interaction between these two, right? Because it's a system of particles, so this will be along the line joining the two. Okay. So the mutual interaction will be such that P1 will be attracted towards or is connected to this by some force, say F12, force on 1, particle 1 due to 2, and P2 is connected to P1 through F on 2 due to 1. Okay, these two are the internal forces of the system. Now let's say some forces, external forces applied to it, a part of it acts on particle 1, let's call this force F1 external force and a part X on particle 2. Let's call this F2. So F1 and F2 are external forces, whereas F12 and F21 are internal forces. This is the system of particles. Now we want to find the center of mass of it. We do not know the exact position of it, but let us say it is somewhere in between the two, and say this is the point where the center of mass lies. Let's call this point C. Okay. So what we mean is that if we consider the whole mass of the system concentrated at this point will move the same way as the two particle system would do under the influence of the net force F1 and F2. Okay. Now let's say the position vector of this center of mass be, let's call this RCM. Position vector of the center of mass. You're with me till now, right? Okay. Now, if we say consider the particles separately, first of all. So, what will be the velocity of V1? V1 of particle 1 can be given by dr1 by dt. By definition, rate of change of position is velocity. This will give us acceleration of particle 1 will be dv1 by dt, rate of change of velocity, which is equal to d square r1 by dt square. Okay. Similarly, v2 will be equal to dr2 by dt, and a2, acceleration of 2 will be d squared r2 by dt squared. This is basic definition of vector representation of velocity and acceleration. Okay. Now, what is the net force acting on? So let's call this external, right? What is the net force acting on P1? Let's say F1 is the force acting on P1. Then it should be equal to F1 external plus force on 1 due to 2. This force and this force both are acting on P1. Right? And similarly, net force on 2, this particle P2 will be F2 external plus F on 2 due to 1. Okay. But this net force causes this acceleration. So Newton's second law will give us m1 into a1 must be equal to f1, and similarly m2 into a2 must be equal to f2. Right? So if we add these two equations, let's say this is equation 1 and this is equation 2. Then if we add these two equations, 1 plus 2, what will we get? m1a1 plus m2a2 must be equal to f1 exterior plus f12 plus f2 external plus f21. Now if you consider these two internal forces F12 and F21, that is this force and this force, they form an action and reaction pair. They are mutually opposite to each other and their magnitude should be equal to each other, which means these two will cancel this out. So what we get, this is equal to F1 external plus F2 external. Why? Since F21 equal to negative of F12, they are action and reaction pair, the internal forces. So what will be left with? That M1A1 plus M2A2 equal to this, let's call this F, the net external force. Fine. So let's take this down somewhere. F equals to M1A1 plus M2A2 and F equals to F1 external plus F2 external. Let's keep this for now. Okay, so this is what we have found by analyzing the system of particles. Now we have said that we have taken RCM as the position of the center of mass, and we have said that center of mass is that point where if we apply the same force, net force, that is F, net external force, if we apply to the center of mass, it will move the same way as the extended particle will move. So if we say the center of mass, the entire mass is to be concentrated, so F will be m into a cm, where m equals to m1 plus m2, the entire mass is concentrated, and acm is the acceleration of the center of mass. Fine. So using this equation that we have found, we can say, therefore we can say that m equal to m1 plus m2 into acm must be equal to m1 a1 plus m2 a2, using this equation, right? So we had just found that a1 and a2 could be written as d square r1 by dt square and d square r2 by dt square, right? So we can write this way, that m1 d square r1 by dt square plus m2 into d square r2 by dt square. Fine. So we have m1 plus m2 multiplied by acm. Sorry, instead of acm can also be written as d square rcm by dt square. Since rcm is the position of the center of mass, so second order derivative of it will give us the acceleration of center of mass, right? acm. So if we rewrite this, right hand side, what we can do is that we can rewrite this as d square by dt square m1 r1 plus m2 r2. We have taken two steps here. First, we have moved m1 into the derivative, because m1 is a constant, it will not change with time. So first term will be d square m1 r1 by dt square, second term will be d square m2 r2 by dt square. Then we have taken the entire d square by dt square common, and we find this. So if you consider left hand and right hand side, what we get? we get d square RCM by dt square must be equal to, we can take this to the right hand side, it will go to the denominator. So 1 by m1 plus m2 d square by dt square m1 r1 plus m2 r2. So if we take this also inside the derivative, we can always do that. Take this inside the derivative, m1 plus m2 into the whole parent, and so this term will be going inside this. So d square RCM will be given by this term. So we can simply write that RCM, the position vector of the center of mass of this two particle system. Now we have found the expression for that. That will be m1 r1 plus m2 r2 divided by m1 plus m2. So this is the expression for position vector, or sorry, center of mass, position of the center of mass of this two particle system. So if instead of two particle system we were given an arbitrary system having, say, n number of particles, similar analysis can be taken and we will get that the center of mass for the n particle system can simply be given by RCM equal to m1 r1 plus m2 r2 plus, keep on adding all the terms till we get the nth term, Rn, whole thing divided by the sum of the masses, m1 plus m2 plus mn. This can be written in terms of the summation notation, sigma, right? So what we will do is that we will say that this will be summation of I equals to 1 to n mi ri divided by summation I equal to 1 to n mi. However, summation this term or this term in the denominator is equal to the total mass. So we can say RCM can be given by 1 by m, total mass of the entire n particle system, not 2 this time, the n particle system will be into summation of I equal to 1 to n mi ri. Alright, now what if instead of having this discrete type of mass distribution, that is where we can identify the mass as particles, that is mass concentrated at different points, right? And we can find the position vector of the different particles. Instead of this, if we had a continuous mass distribution like this duster, you can see here it's difficult, so many particles are there, it is not possible for us to find the position vector for each and every point and to find the masses of each and every particle. So instead of having discrete mass distribution, if we have a continuous mass distribution, not discrete, if we have a continuous mass distribution, then what we will do, what we are going to do. So let us say we have a body, there are huge number of masses distributed, right? The entire mass of the body is distributed all over its area, volume, right? So we do not know how to find each and every particle. So what we will do to find the center of mass of such case, we will consider a very small volume and find its position vector. Say and let's say the mass of this small elementary volume, so small that in the limiting case where dx, dy, dz, the three-dimensional, three sides of the cuboid will be going towards tending towards zero, very very small, and let's say this is its mass is dm. Okay, so instead of m1 r1 we will have now r dm, r multiplied by dm, and then what we will do, we will integrate it over the entire body. If we integrate it over the entire body, we will get the equivalent of summing the mi into ri over the entire discrete body. So for a continuous body, what we will do, instead of doing the summation, we will integrate it over the entire body of the object, or discrete continuous mass distribution. Now we have found this term. So by definition, RCM will be 1 by total mass of the body multiplied by this. So in case of continuous mass distribution, this will be the equation: 1 by m integration over the entire body of the continuous mass distribution R dm. Okay, now in this case, if we choose the system such that, or the coordinate system, see, coordinate system is our tool, so we can always choose the coordinate system, and we try to choose, or we have chosen, let's say we have chosen the such a coordinate system where RCM, position vector for for the center of mass, turns out to be 0, or at the origin. So if the center of mass turns out to be at the origin, then RCM will be 0, will be a 0 vector. So which means 1 by m cannot be 0. So from this equation we get integration R dm will be 0. Or if we say R dm has to be 0, then in terms of its components, see, R is a position vector, so it will have x, y and z components. So we must have the x component, that is x dm, the y component, that is y dm, and the z component, that is z dm. All of these must be equal, and they must identically be equal to 0. So if the position vector, or sorry, if the center of mass is at the origin, all the three terms will be identically 0.